So part of getting you ready for a year of geometry is to prepare you for the type of shape we study most often, which is the polygon. And by the end of this lesson, you should understand what all of these different vocab words refer to when we're talking about polygons. So not all shapes are polygons, so let me help you figure out what makes something a polygon. A polygon is a closed plane figure formed by 3 or more line segments, each of which intersects exactly 2 other sides, one at each endpoint. That last part is a little hard to understand, so we're going to go through that as an example. We'll also note that the endpoints are called the vertices of a polygon. So we know what a vertex of an angle is. The vertices of a polygon are just those corners. First thing I'll explain is what is meant by a closed plane figure. Remember, planes are flat, and closed has another meaning. So a plane figure means that this needs to be flat. A cube would not be considered a polygon because that's more 3D. It has to be just on a plane. And closed means you can't start drawing something and then stop short. That would not be considered a polygon because there's an opening in there. The next part is it's made up of 3 or more line segments. That just means that we're going to be looking for straight sides, no curves in a polygon. And like I said, this last one is kind of worded tricky, but let's do an example to understand. So A right here, it almost looks like 2 shapes put together, and that's a key that we're not looking at a polygon. Let's just look at one of the sides right here. Let's look at this side. It says that each side intersects exactly 2 other sides. Well, I'm actually seeing that this side touches that side, so does this line segment, and so does this line segment. So that rules it out right away because we are not allowed to have 3 different line segments touching that. Also, we're only supposed to have 1 line segment at each endpoint. So this is just an example that's not a polygon. And it's basically because of that middle thing that's kind of crisscrossing in there. So a polygon just has to be made of line segments that outline a shape. The second one, I would say it's closed. I would say it's flat, it's 2-dimensional. It's made up of nice straight line segments. And if we look at each segment, it's just intersecting 1 at each endpoint, 1 other side at each endpoint. This one is a classic example of a polygon, pretty standard shape, everything has straight sides. That's a polygon. This next one, do you see the violation? It's flat, it's closed, it's just connected, there's no crisscrossy parts, but it's the line segments that's violated. That right up there is not a line segment, is it? It's not a straight line segment. And so we would say this one's not a polygon because it has that curve at the top. And now this sort of plus sign cross looking thing, it's closed, it's flat, it's made of straight sides, and does each of those sides touch 2 other sides, 1 at this endpoint and 1 at that endpoint? Yes. And so again, it's just kind of an outline of a figure using straight sides. That is a polygon. A triangle is a great example of a polygon, and I want to talk about how we name a polygon. Remember that we were naming planes using 3 points that make a triangle. So when we name a triangle, we can use those 3 points that make the triangle, but we'll just put a little symbol on the front that indicates we're talking about the triangle, not the plane. And the order shouldn't matter on here. It's not like we're naming an angle or anything, so any order should do. Now when we go to a polygon that has more vertices, this one has 1, 2, 3, 4, 5 vertices, the order does matter, just a little bit. The order has to be consistent. I can't go from B to D to A to C to E to B or anything. I would need to go in order. So if I wanted to call that polygon B, C, D, E, A, that's fine because I'm going around in order. So the order only matters in that way. I could go E, D, C, B, A. E, D, C, B, A. So clockwise or counterclockwise doesn't matter. And if you wanted to be more specific, maybe it would make sense to write pentagon, B, C, D, E, A. But if you're listing that many points, it's just assumed that you were talking about the polygon that's outlined by those vertices. Now, naming a polygon is different from classifying a polygon, and the rest of this video is going to talk about how we categorize or classify polygons. One way to classify polygons is to determine whether they are convex or concave. And I think the book's definition is very specific, but a little bit confusing, so I'm going to try my own method. When I hear the word concave, I think caved in, like it has dents. This one is a concave polygon because it's dented in from the outside. Where this one doesn't have any indentations, everything is sort of fully inflated, right? On these other examples from your book, can you see that that would be considered caved in to me, so that's concave, where this other one, fully inflated. There's nothing poking into the shape. Another way that I remember this is I think about a bear. A bear wants to go into a cave, but he's wandering around here and he can't find anywhere to snuggle up because there is no cave. This is a convex shape. Where this one, he wanders around and he finds this cozy little nook right there. That's his cave. Or right here, you can find a little spot to sleep, right? So there's little dense little caves where the bear could sit. Another way to explain is to use the rubber band test. If you stretch a rubber band around your polygon and it fits nice and snugly, that's a convex polygon. Where if you put your rubber band around your polygon and there's some gaps in there, that's concave. And you know what a nice thing to do with those gaps is? Let a bear stay in there, in the cave. We can also classify our polygons by the number of sides. I think everybody knows this one. Let's quiz ourselves as we go. A three-sided polygon is called a triangle. Four-sided, kind of a long one. It's not just a square or anything. It has a more general name. Quadrilateral. Five sides is a pentagon, kind of like the Pentagon in DC. Six sides, hexagon. Seven sides, this might be tough for you to remember. You might have studied that one a little bit. They call it a heptagon. Some people might also call it a septagon, which I would also accept. Eight sides, you might know this one. Eight sides is an octagon, like an octopus has 8 legs. 9 sides, people don't talk about these much, but a 9-sided polygon is called a nonagon. 10 sides, I think this will make sense because there's 10 years in a decade. There's 10 Hail Marys in a decade. This one is a decagon. Decagon. They skip 11 for some reason, but what they call an 11-sided one, just FYI, is a unidecagon. Like a unicorn, it has one extra side than a decagon, so unidecagon. And then a 12-sided one, we use these a lot. 12 sides is 2 plus 10, so dodecagon, like Spanish, dos, 2 plus 10, dodecagon. Now, if we ever go above 12 sides, let's say something had 42 sides, do you know what you'd call that one? For anything that's bigger, we call that an n-gon. So a 42 side would be called a 42-gon. They just don't even bother trying to make names for them. I think technically there are names that you could Google for them, but if it's above 12, you just go ahead and call it an n-gon. 15 would be a 15-gon. Another way to classify polygons: equilateral, equiangular. Equilateral, equa, meaning equal. Lateral is a word that means side. Maybe you can think of a football term or a physiology term where lateral could mean side. Equilateral means that all the sides are congruent. So I have a polygon here and all of the sides are the same length. How would I mark that? I would mark it as tick, 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 tick. And if all of the sides have exactly the same length, I could classify this as an equilateral polygon. P.S. Do you see these little dents in there? It's also concave, isn't it? This one's concave. Equiangular. This one's a little easier to remember. Equa means equal and angular means angles. So all the angles are congruent. So how do we mark angles congruent? Swoop. Swoop. All of these angles would have the same measure if we stuck a protractor to them. So a polygon that happens to have all of its interior angles congruent, we call that equiangular. And finally, some polygons can be classified as regular. That name is sort of disappointing to me because I think these are the best type of shapes. They're not just regular, they're amazing because they're convex polygons that are both equilateral and equiangular. They're so pretty. Look at this pentagon. It is equilateral, all the same size, and equiangular. What a fantastic specimen. And it gets the classification of a regular pentagon. Let's look at these examples. A here, are all of the sides congruent? Then it's equilateral. All the angles are congruent. It's equiangular. Therefore, this is a regular polygon. A regular hexagon, you could say. This next one, looking kind of like a parallelogram to me. I see that I have some congruent sides and some congruent angles, but only these two sides match each other. And then these two sides match each other. But in order to be equilateral, all four sides would have to be the same length. So I think we fail already. And then the same thing with the angles. These two angles match, and those two angles match with those double swoops. But that doesn't make it equiangular because we'd have to have all four angles the same. So this one's not regular. This last one is kind of controversial. I see lots of ticks. I think all of those sides are the same length. And it looks like I have a ton of right angles too. Aren't they all right angles? Unless you consider these inner angles. You know what I mean? Like that would be almost like a 270-degree angle or something. So that's why they include the word convex in the definition. Do you see the caves in this shape? They would not consider this one a regular polygon. But the sides are all equal. Equilateral. I don't think I would go with equiangular because I don't like that the inside angles aren't all 90s. So I'm not going to go equiangular on that one, and therefore I'm not going to call that regular either. You did it. You made it to the end of this lesson. So do you think you can identify what each of these classifications means to us? Convex, concave. Can you tell the difference? Can you memorize the side classifications? Triangle, quadrilateral. I'd like you to know them all up to 12. And then equilateral, equiangular, and regular. Classifying polygons.